The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. My name is Emily Kuda, and I'm Percona's Digital Marketing Manager. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, please raise your hand using the hand icon located in GoToWebinar, the control panel, to let me know if you can hear me. Okay, great. Now, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible. Those that aren't addressed will be answered in a follow-up blog entry on Percona's MySQL Performance blog. In addition, a recording of this webinar will be made available to everyone within 48 hours along with the slides. I would like to thank everyone for attending today's webinar, Scaling MongoDB, Avoiding Common Pitfalls, presented by Jon Tobin, Percona Senior Sales Engineer here at Percona. With that said, I'll turn the floor over to Jon.
Thanks, Emily. I appreciate it. As Emily said, welcome everyone. Good afternoon here in Boston. I'm Jon Tobin. As Emily said, I came over to Percona when they acquired Tokutech back in the spring of this year. So I have probably about 2.5 years of experience in MongoDB. Before that, I was working in the enterprise storage market, working for EMC. So I know quite a bit about storage and its interaction with databases. But let's get into why you're here, scaling MongoDB. Just a quick look at the agenda for today. This is just high-level bullet points. We'll go over a little bit about document design. We'll talk about data management strategies, which are very common in MongoDB. We'll talk a little bit about replication and failover. And if we have time, we'll get to sharding. If not, as Emily said, the slides will be available. There will be a blog post. You can comment. You can email me, whatever you need. We're always here to help. So let's get a little bit into document design. So a little more detailed, we'll talk about what's different about MongoDB, why that lends itself to a little bit different design. We'll talk about embedding things versus referencing them. So, talking about denormalization if you're used to the SQL space. And we'll talk kind of about the gray areas and how a lot of the truth lies in between, you should say, or in the margins, as people like to say. So document design, this is the by far most common source of confusion and also substandard performance in MongoDB today that I've seen anyways. And the reason is that people think of databases in the traditional relational database way. Everything is normalized, right? Fourth normal form, all tables relate to each other. And MongoDB and most NoSQL databases were founded on a principle of doing things completely differently. So throwing away the relational model and starting things differently, that's why they're called NoSQL databases. The thing that's different about them is, in MongoDB's case, is a dynamic schema. People like to think there's no schema. It's not that there's no schema, there's just no enforced schema like there normally is in relational databases. And it's meant for agility, flexibility. That's one of its biggest things, but that doesn't mean that you don't need to design your documents carefully, because there kind of is a schema in there. Your application expects certain things of the documents contained in the database, usually. That's one of the foundations of good application design. So the two kind of have to go together. And you do have to make design decisions. Not only that, you have to live with the decisions that you make later on in the future, because it's hard to change the document design and to tell your application that it's going to be working with multiple versions of documents, and each version of the document may contain different things. It's hard to do that in the future. So if you make some careful considerations today, then you can live with those going forward in the future. But not only that, you have to realize that there are positives and negatives for the document design that you have chosen. And understanding both those positives and those negatives will allow you to scale your MongoDB infrastructure in the future efficiently and easily. And those are two very key things when talking about MongoDB at scale. It is NoSQL for a reason, so get comfortable with the fact that denormalization is common, right? It's not a bad thing anymore. You can do things differently, so don't be afraid of that. However, not everything has to be denormalized. Like I said, there's a gray area. The truth lies in between. So not everything is denormalized. And so let's talk a little bit about that. So here's a little quick and dirty document design pointers. I've just taken kind of a quick use case. It's useful for this discussion. If we were talking a little bit about a collection we are going to design for, let's say, a college, and I was a student there, this may be how I would lay out documents. So if I wanted to embed things, you can look at the first one on the top right. We have our underscore ID, which is just like the identifier, the primary key of the document, first name, Jonathan, last name Tobin, year 3. In this case, I'd probably be a junior. And then classes, if we were going to embed, we would embed our classes right in an array in that document itself, right? So I could just say, I'm Jonathan Tobin. I've taken Calc 101. I may take English 101 and several other courses as well, maybe like Psych 101, and they would all be embedded right in my document. And it's great because when we go to query that document and find out, hey, what classes has Jonathan Tobin taken? Because maybe we're trying to put a report card together or something, or his transcript. I can grab all those documents right in one query, right? I don't have to go reference anything else. I can just look down, hit that array. Yeah, great. Calc 101, English 101, Psych 101, got all those. And this is awesome for query performance, right? It's nice and easy, but I am replicating a lot of data for every single user, so it's not always perfect. And it's great when fields are static, meaning they don't change a lot or they don't grow unbounded, right? In this case, this may be a good way to do things, right? A student probably isn't going to take 1,500 classes. They may take 30 classes. On the high end, they may take 50. Say they go for a doctorate to maybe 80 classes, let's say. It's not unbounded, so it's not social networking. So you actually can be able to reasonably determine the size of this field and thus the size of the document. And that's so documents aren't kind of getting migrated all the time, right? The background migrations, especially if you're using the mmap engine, are a subject of great performance issues in the past. I'm sure there's probably people out there that have seen them with document migrations because they're growing too fast. The amount of space that has been allocated by the memory map engine isn't enough for the document anymore, so it has to migrate it to a new chunk of space that's big enough for the document. The last bullet point here in embedding is talking about eventual consistency. And what that means is that, so I have Calc 101 in my document. The next student probably took Calc 101 too, and there may be, 300 students over the course of the history of the college that have taken Calc 101, and it exists in all their documents. Should I need to change, let's say, the number of credits in this case for Calc 101, I have to go into every single student's document and change the number of credits for Calc 101, right? It's kind of an overweight operation. But number 2, atomicity is only guaranteed in MongoDB today at a single document level. So I can only guarantee that one document gets changed at a time. So this operation may go halfway through the documents and fail. So 150 kids now have, Calc 101 is having 4 credits, and 150 kids still have it with 3 credits. And I have to go and figure out a way of finding which kids don't and changing their documents to 4 credits now, right? That's difficult. And eventually it'll be consistent, but it's not necessarily consistent when I fire off that first database operation to update the number of credits. That's what we mean by eventual consistency. So let's look at referencing, right? When does referencing make sense? So we'll look at the exact same use cases. And instead of putting the actual class right into my document, right, I'm going to reference the object ID of basically a collection of record, right? And the collection of record is probably going to be a classes collection. A collection is just like a table in SQL databases. And inside that classes collection, we have a different document with a different object ID for every single class. And so this is great when we have insert performance as a priority, because I'm constantly just inserting in one place, right? They're quick and efficient. If updates are common, like I said, we want to change the credits, we only have to change it in one place, right? Everybody references that one place. So now everybody, when we want to see how many credits they got for Calc 101, we just go back to the Calc 101 document. We see now it's 4 credits, right? Everybody references that document, so we're all set. This is great when immediate consistency is necessary for the same reason, because the update only lies in one place. It's also going to be an atomic operation. So when it completes, we know that it completed everywhere, just in that one document, single document atomicity. And this is also nice when the field size can't be determined. So you heard me talk a little bit about social networking in the future, so we can talk quickly about a case where this would be common. In social networking, let's say Facebook, I have a bunch of friends, and I don't know how many friends I have on Facebook, but let's just say it's 120. I'm kind of a loser, so it's probably lower than that. But I have 120 friends. Donald Trump, well, he may have had a lot of friends before. They're probably fewer lately, but you know, he may have 5,000 friends, and Ben Affleck may have 10,000 friends. Maybe that was poor choice of people to talk about, but the point is that every particular user of Facebook has a different number of friends, and the range of the number of friends that we could have is huge, right? It could go from 0 to, I mean, almost infinity. What is there? I don't know. There's what, like 6 billion people on the earth? I guess it could be that high. I don't know how many people Facebook has as users, but the point is it could be huge, and there's big differences in between. So referencing something that contains all of those friends is probably a better idea than trying to embed it right in a user's document, because it's going to be unbounded. It's going to be hard for us to maintain any sort of performance when we have a bunch of documents with huge differences in their size. Not only that, we might not always want that information when we go to a document, so it may not be a good idea to have it stuck in the document. If we want it, we can reference into it and go find it if we need it. But as I said, the truth often lies somewhere in between, right? It's not about embedding, it's not all about referencing, it's about doing a little bit of both depending on what works for your use case. There isn't a right answer. It's not black or white. It's pretty much always gray with MongoDB and NoSQL. So here are a few tips. Embed fields that are often fetched, right? So if you normally go to somebody's document, you know, in this case, we can use the same student thing, and you get classes, then maybe it's a good idea to embed them. It might be. But it's not a great idea to embed them if they grow boundlessly. We already talked about social networking. It's hard. If you can't determine that, I wouldn't recommend putting them in a document. Instead, reference them. Reference somebody's friend's document. You know, maybe you have to reference more than one document to them to try to keep the document to certain sizes. You know, maybe a document can only contain 1,000 friends, and you have a few references to a couple of documents with the friends in them. So limit growing keys. You know, if you do have keys that grow big, don't have usually more than one per document. Just because it's hard to determine the size of those fields. And not only that, they can be performance limiters, growing keys can. So if you're going to have one, try to limit it to 1 key per doc and move that to the last key in the document. So instead of having it in between where every time it grows, I have to rearrange the documents and all the keys that come after it, instead I'll put it as the last key and I can just append onto that key or onto the end of the document. That's a more efficient way of doing things. So try to move them to the last key in the document if you can. reference fields that are volatile. So if you do a lot of updates to a field, you may want to reference it so you're not constantly updating a document that doesn't need to be updated, because maybe I'm doing queries on that document. And if I'm also doing updates on it, then I'm going to have a locking conflict there. So if I can update a reference field, then technically I get 2 locks for that same document. As I talked about, in MongoDB, atomicity can be achieved at a single document level. And a lot of people come from the relational database world, and they're used to using transactions. So they try to engineer these extremely complex documents so they can do these atomic updates to them all the time, and it's a real performance limiter. If you need atomic updates, then maybe you would be bounded to that, but chances are there may be something else, another database, that's better for your use case. MongoDB is not perfect for everything, and you may have a better solution for that. If you are going to do like a document design like that to get atomicity, take care in your design. Right? Really think about what you're doing. Also, there are some other alternatives out there. I came from Tokutech. We have TokuMX. It's ACID and MVCC compliant. So we actually do have multi-document transactions in MongoDB. It's a fork of MongoDB. You can go now. It's part of Percona. You can go and take a look at TokuMX, see maybe if it fits your use case. Indexing. So index judiciously. I say that because indexes tend to be, they're basically database work multipliers. Every time you insert documents, you have to maintain all the indexes that reference that document. And it can be difficult at scale when you're doing things concurrently, especially with things like B-tree indexes, which are in WiredTiger today. They're kind of part of the basis for mmap as well. They have serious problems with index maintenance, and the more indexes you put in, the more overhead your database is going to have to maintain those indexes. So use indexes. They're great for queries, right? But think about the indexes you're putting in and whether or not they're useful, and reevaluate that often. Drop the indexes that you don't need. Obviously, you can add indexes that you do need because your queries should be covered by indexes. Queries that are querying the full collection are not going to be performant, and they're going to cause problems for the rest of your database. So do use them, just use them judiciously. Store relevant data. This is actually a good segue into the data management aspect, but archive old data when possible, or delete it if you don't need it. MongoDB databases I've seen just grow enormously. I mean, they get huge, they really do, and they go beyond the bounds of what anybody ever thought they would. So if you can get rid of data or archive it to somewhere else, I would recommend that you do that, and develop your strategy early as well. But with that, let's segue into data management. So we'll talk about the why and how of data management, the details and uses in MongoDB, and some other options. But data management itself, why, I talked a little bit about the amount of data that goes into MongoDB. It really does grow. But a lot of people like to put ephemeral data in it. They like to do things like logs or sensor readings, I say here. And there's a lot of information going into MongoDB very commonly, in most common use cases, that has a window that is expiring. At some point, it's just really not going to be useful to us anymore, or its usefulness is going to be extremely diminished. That'd be something we could archive. But if you want to actually get rid of it, there's a couple of things, a couple of built-in features of MongoDB that you can use. And people like to do this for space management sometimes, and sometimes it's also for performance. With WiredTiger, I've seen some good things with cap collections. I've actually seen performance accelerations, although I haven't done much testing and I have never seen it in the wild be more performant. So I don't want to say anything definitive, but WiredTiger may actually be a little bit faster with cap collections. mmap, not so much. But the options in MongoDB are TTL indexes, which are time to live indexes, cap collections, In TokuMX, we implemented a feature called partition collections, which is just like partition tables in MySQL, if you're familiar with that. And you can also do something I like to call ghetto partitioning. We'll talk about all those in the upcoming slides. But let's talk about cap collections first. Good thing is they're super easy to use, right? In the Mongo shell, you can just say db.create collection. In this case, we would create a collection called test. We would set capped to true because we want it to be a capped collection. You can set the size to a certain size in bytes, whatever that may be. And you can also optionally set a maximum number of documents to contain in that capped collection. So in this case, what we would get is either a collection that hits the maximum size, so the cap size, or the maximum number of documents, whichever comes first. And it's within a reasonable range. It's never going to be exactly that. Maybe a little bit smaller, maybe a little bit bigger. It depends. One thing to know, though, is that MongoDB is going to use all that disk space right away from jump. So you have an empty collection, but if you choose 10 gigs in size, it's going to take 10 gigs of data, 10 gigs of disk space right away, because it wants to use that for, I believe, for performance. So the cool thing about cap collections is it automatically drops documents. It just pushes them right out. It's basically like a rotating circular buffer. It maintains insertion order and just pushes things out at the end. So new documents come in the front. The old documents, based on insertion order, go out the back. The other great thing is that it's really easy to tail the op log. This is basically the way replication works, actually, in MongoDB. Basically, your secondaries just tail the op log of the primary. So the op log is a cap collection, and the secondaries just kind of read off that collection, and they replay on onto themselves. Some of the bad things about cap collections are that there's no sharding, right? So if I started with a single replica set and created a cap collection, and for some reason I want to shard in the future, I can't do that. Cap collections are not shardable. There's also a limited ability to update docs. Documents cannot grow in a cap collection. Not only that, cap collections can also, they can possibly break replication because of the fact that documents in a cap collection can grow and, well, they don't really grow. They actually shrink, and then they can grow back to their original size. That's actually kind of allowed in a cap collection, but that can break replication sometimes. So, you may want to think about where you're actually going to use your cap collections. There's also no deletes on cap collections. Because they're that circular buffer, the only thing that can let a document out of the collection is for it to be pushed out of the collection itself. And their performance can be extremely unpredictable at scale, especially with queries. And the problem really is secondary indexes. And when the buffer actually gets to the defined size, that maximum size that you define, and it starts to push documents out, you see really odd performance characteristics, and they seem to be completely unpredictable. All of a sudden, things will be going really fast, and they'll slow down to nothing. You'll start getting timeouts, especially on your queries, maybe even your inserts, and then they'll speed back up again, and then they'll stop. It's really bizarre, and it's hard to predict. So if you need something that's really performant, and perform it in a predictable way, you may want to think twice about using a cap collection. Sorry. So we'll talk a little bit about TTL indexes. TTL stands for time to live indexes, but we'll talk a little first about the internals. The TTL requires an additional index. So instead of being a collection type, it's just a regular collection, but it has an additional index, and it can be a single key only. It has to be the bson date type field. And like I said, it's single key, so you can't actually say, I want a date. Also, I want it to be on first name and last name. you couldn't use that for a TTL. It could be a secondary index, but it can't be the index you use for the TTL. It has to be date only field. And what it does is it uses a background thread that runs on every single member of your replica sets. And this background thread runs every 60 seconds. And I mean every 60 seconds. It's not configurable. You can't change that value. It runs every 60 seconds. So what the thread actually does is it queries the full collection by the TTL. So it's actually only scanning the TTL index itself by date until it needs to find, or until it finds a document that it needs to delete. And it deletes every doc. I understand this is a little hard. It was hard for me to write down. It's kind of hard for me to explain it too, but it deletes every doc that has a time that's greater than the amount of time you define for documents to expire. That's what expire after seconds is. And it deletes every doc that has a time that's greater than expire after seconds, whatever that value is, older than the current server time. So basically, if I set expire after seconds to 600 seconds, 10 minutes, everything that's older than 10 minutes older than the current server time would be deleted by the TTL thread. And what it does is single document deletes. So it goes, looks for a document and then deletes it. Looks for the next document, deletes it, right? So the single document deletes are not really efficient ways of getting things out of a collection, but they're effective. The deletes work. The docs are only deleted from the primary in the replica set, even though the thread runs on every secondary. So it's kind of odd. The thread isn't particularly impactful, but it does use resources and it uses them on every secondary, even though it's not going to be deleted. The deletes only happen on the primary and then they're replicated to the secondaries. So the great things about time to live index, it's easy to use just like cap collections, right? You create a regular collection, you tell it that you want an index on a date field. In this case, the date field would be called mod date. So I tell it I want an index on that, and I want it to expire documents every 600 seconds, so every 10 minutes. And it's automatic expiration of the documents. However, the documents aren't guaranteed to be deleted at any one time. When 10 minutes is up, they're not necessarily going to be deleted. It may be 11 minutes, it may be 15 minutes, who knows. At some point in the future, when the thread gets to it, they'll be deleted, but they aren't deleted immediately. The bad thing, as I already mentioned, is that it's a query and single document deletes, which are not efficient. And if you just want to do some easy math down at the bottom, if you're doing 1,000 inserts per second, which isn't even high, that's not a high, and you set a particularly low expire after seconds, 10 minutes is pretty low, so 600 seconds, I have 600,000 single document deletes to do on my primary, which is probably going to interrupt my actual production workload. So it can be impactful, right? So these single document deletes are actually hard to do, and this thing isn't schedulable, right? It just all of a sudden kicks off and goes. So it can be impactful to your production environment to delete this information. And so other options, like I said, partition collections in TokuMX. The reason why we implemented this feature is because we came from the MySQL space. In MySQL, there's partition tables. Partition table just basically breaks up data into its own file by the partition key. So in this case, it'd be by date, and it just sorts the data into files. And those files are quick as like RMing, removing a file in Linux is, right? It happens split second. And not only that, we only have to pay that remove penalty once, and it's a very small penalty for however many documents are in that file. So, you know, it could be 1,000 documents deleted like that, right? It's not an actual scanning delete like the TTL thread is. And so basically what you're getting is a batch delete. And so what I call ghetto partitioning is basically the same thing. It's you would change the collection that you're inserting to based on the time. So I would be inserting in one collection for 10 minutes, then I would switch over, start inserting in another collection for another 10 minutes, and then switch over and start inserting into another collection 10 minutes. It's difficult to do because you have to put that logic into your application. And then you have to stitch your collections back together whenever you want to query across collections, because there's no joins in MongoDB. So I have to know which collection I'm going to query. I have to grab that set, I have to query another collection, grab that set, and then stitch everything back together. Keeping track of all that stuff is pretty hard to do. But dropping a collection is very efficient, especially relatively speaking to the way it's done in a TTL index. So here are some TTL tips if you do want to use them. When adding TTLs to an existing collection, be careful of the very first run. People surprisingly really tend to forget about this, but they may all of a sudden decide I want to put a TTL index on a date field that I have existing in a collection that I've had for several months or a year, and I'm going to set the expiration seconds to let's say 10 minutes again. Think about how many documents are already in the collection that need to be deleted, right? When that TTL thread runs, it's suddenly going to have, it could be a couple million documents, maybe more than that, that it needs to delete, and that's going to impact your production environment seriously. I can tell you that. And I've seen scenarios where it's happened on a Friday night, and that leads to a really, really bad weekend for whoever the DBA is or for the application developer. So you got to find a way to actually get those documents out slowly before you define that TTL index, if that's your case. Another thing, monitor your disk utilization closely. Most likely your disk is going to be the bottleneck when you put in a TTL index. So monitor your disk utilization closely. And if your IOPS start to get high, your TTL thread's only going to add to that. So increase your resource pool, increase the number of IOPS that you have available is one way of scaling and getting past that. Another way is to shard, to just get less data for each TTL to look at. And that also depends on the shard key. That can be kind of hard sometimes. So there's a couple of ways to get around it, but TTLs do require some very careful design if you want to get them in a performant manner. Keep an eye on fragmentation also. This is a huge problem with the memory map storage engine. The TTL key itself is a secondary key, and it points back to the primary key, which is usually the object ID, the underscore ID. And it's a random workload. So it's deleting documents randomly from in there, usually. It depends, of course. And so that leads to fragmentation, and that can make disk space balloon up sometimes. You can also consider using an expire at field instead. So instead of doing an expire after seconds, you can set that to 0, and you can put an expire at field instead of your documents. And what this does is it gives a time for expiration. And this basically allows you to schedule the period during which the TTL thread will actually delete. It's still going to run every 60 seconds, but it won't delete any documents until it hits that expire at field. So, say midnight is a really slow time for you guys. You set the expiration date that you want for that to expire at, let's say 11:58, and right around midnight when that TTL thread kicks off, it's going to actually delete that document. So you can kind of set the time at which it does the deletions. Obviously, it runs at any time. Check out the prezo. I have some resources slides after each section in this presentation. They're hidden, so you won't see them now, but the actual slides themselves will be available. And there's a link in there to a presentation by Kim Wilkins from Object Rocket. She has some great tips on TTLs, the math you can do to kind of figure out how they're going to perform, and also how you can implement them in a performant way. And I think she also has some GitHub links to some code and stuff to help you out. It's a really cool presentation. Kim's really smart. So that's my lowdown on data management. Now we'll get into durability and high availability. Mongo's awesome, has replication built into it, super easy to set up a replica set. It also has the election protocol for high availability. So, if your primary does go down, a new primary gets elected, cool stuff, right? So we'll talk a little bit about the life of a write, durability in MongoDB, how all of these things kind of affect replication, and also talk a little bit about some of the considerations along your journey that you need to think about when using write concern and replication. So life of a write real quick, this is pretty basic, but your application sends some data to MongoDB. MongoDB receives it, applies it to memory, will apply it to the journal if you've chosen to use a journal. That is optional. I usually recommend using one, but you can obviously run without it. It'll write it to the data file. It'll apply it to the replication journal or the op log, right? And in MongoDB, there is a write concern, and write concern basically allows you to determine the strength of guarantee or the amount of durability that you want from MongoDB. And the default is acknowledged. So that's once it hits memory on the primary, you get an acknowledgement back to the server that I've done what you've done, or I've completely failed, either or. But realize that in that case, it would only be in memory. It's not actually durable and down on disk. And obviously, I've already said the acknowledge of write depends on your write concern. So in replication, you have primary and number of secondaries. It could be as many as you want. And every shard consists of one of these replica sets. Each replica set has a primary and secondaries or arbiters. An arbiter is just a member of the cluster that votes, but doesn't actually contain any data. Secondaries read the primary's replication log and they apply it to themselves, but they do it asynchronously. So this isn't synchronous replication. There usually is some amount of lag going on. So replication lag does tend to be a problem in MongoDB. A lot of people run with at least a little bit of replication lag, depending on their setup. And you can run the RS status helper will get you the current replica set config, and the replication information will also tell you things like lag, things of that nature. And replication lag affects durability, it affects elections, and it can definitely affect write throughput depending on write concern, because you could set your write concern to say, I only want to be acknowledged. I only want any write to be acknowledged or any change to the database to be acknowledged once it hits one of the replica sets, or maybe a majority of the members of the replica set, right? In that case, replication lag is going to affect when the acknowledgement gets sent back to the application server. So why does replication lag usually happen? Well, one, your primary has concurrency, right? With WiredTiger now you have concurrency. Even with mmap you have slightly better concurrency. With TocoMX, since day one, you have had a document level lock, so huge amounts of concurrency available, especially with TocoMX and WiredTiger. And replication is single-threaded, so this is a common problem in MySQL as well. You have this huge wide pipe with concurrency going into your primary, and what is basically a trickle coming out of your primary going to your secondaries. So sometimes replication can be overloaded. Sometimes you get high resource utilization on your secondary. Sometimes people run secondaries that have slower disk, let's say, than their primaries. And so there's just less I/O available for the secondary to replay operations from the primary's op log. So what happens there is I get a bottleneck at the disk, right? I can't replay operations that fast, so I'm just kind of queuing them up for replay on the secondaries, and therefore my secondary is lagging behind my primary. Also, there can be network latency issues. I'm sure we've all seen problems with network latency. And so obviously the packets have to get across the network to the secondary. So sometimes that can affect your replication. So some tips, tricks, concerns. This is a little smorgasbord. But lag affects everything we've kind of talked about so far. If you're doing 1,000 inserts per second, you have a 5-second lag plus an election. So plus you're trying to elect a new primary. That could be 5,000 inserts that have to get rolled back on that primary. And the reason is, so my primary takes all of these inserts, right? And due to write concern reasons, say I'm just using default acknowledge, the application servers think those 5,000 things have gone into the primary. but the primary goes down before those 5,000 things have gotten replicated to its secondary. All of a sudden, the secondary server gets elected as the primary, and at some point in the near future, the old primary that was demoted now comes back into the replica set and gets promoted to the primary. All of a sudden now my primary has 5,000 documents that the secondary that was primary doesn't have. Those 5,000 things need to be rolled back, and so that's a problem. Now you have to figure out, okay, somehow I got to get the application to either put that stuff back in, or I have to let the application know that those 5,000 things actually don't exist. That's tough, right? So always try to determine the source of your replication lag and eliminate it. It can be a problem. It's not a problem when you're running perfectly fine in production, but at the time you get that election or something unexpected happens, right? The replication lag can come back and bite you in a pretty significant way. And at that point, your life is already going to be pretty hard, probably, trying to determine whatever happened. And then once you solve it, now you got to figure out what's happening with all these documents that got rolled back. So that can be a serious problem. So I recommend that you always try to eliminate replication lag whenever you can. The most common cause that I've seen is single-threaded replication. That's the most common cause for replication lag. And single-threaded replication. So, always double-check your network latency in between your hosts to try to rule that out. It's fairly common, but it's not usually what I see the problem being. Usually it's single-threaded replication. It's getting a singleton process like that per MongoDB instance. And so the solution is often, in this case, is micro-sharding or sharding in general. But what I mean by micro-sharding is having more than one MongoDB per physical server. A lot of people tend to buy these big, huge honking servers, and they have a lot of resources available to them, but you'll only get this singleton process. You only get one replication thread per MongoDB. So you have all these resources waiting to power this tiny little pipe on the back end, and it's causing all this replication lag. So in that case, just actually provision more MongoDBs on that physical server and shard your environment, but just do it on one single server, right? So you can do things that way to kind of get more throughput. Or you can shard out on more servers if your servers aren't that powerful. But that will give you more replication threads, and therefore give each replication thread a little bit less to do. So if you shard in an intelligent manner, you can get better replication by basically parallelizing it through sharding. In TokuMX, it has a feature called read-free replication. And basically what read-free replication does is it uses the fractal tree, which is our patented indexing, to actually speed up how fast your secondary can replay the op log of the primary, and it does it by turning it into just a straight insert stream. Basically what we do is we tell the secondary, hey, this is what the document looked like before, this is what the document looks like after the changes were made. Just create an insert and put it into the secondary, and we can do that at cache speeds because it's a right optimized data structure. So it can dramatically speed up the efficiency of your secondaries in your environment when using TokuMX. There's also a resources slide, by the way, after that that's hidden that you'll be able to get when we distribute the slides. So sharding and balancing, I may not get through all of this. I know we're running kind of short on time, but I'm going to at least start it. So I'll give you some setup tips, tips on shard keys, a look into the balancer. Like I said, all these will be available afterwards. If you have any questions, I'm always free to help out. So some setup tips and gotcha. Always make use of multiple config servers. Config servers are the brains of any sharded environment because they tell the MongoS, the sharding routers, where all the data lies. So which replica set contains the data, and the sharding routers use all that information from the config servers to actually route database operations to the proper replica sets. 3 is a safe bet. Mongo says absolutely you have to run 3, which isn't necessarily true, but they tell you that for a reason. So I highly recommend run 3 and back them up regularly. If your config servers go down and they're unrecoverable, you're basically you have to recover the position of all the data manually. It would take you a pretty long time, and you can avoid it easily by backing up your config servers. So back them up regularly. They're pretty lightweight. Run them. Just don't run too many, but 3 is a good number. One MongoS, one sharding router per app server is a great way of working. I've never seen that fail, so highly recommend you do that. When converting from a single replica set, remember to point all your application servers to the MongoS sharding router and not to the primary anymore of the replica set. This can be a common problem, and going around the MongoS will cause all sorts of consistency issues in your cluster. So remember, as soon as you go from a single replica set to a sharded setup, remember, repoint everybody to the MongoS and prevent app servers in the future from connecting directly to the replica sets themselves. You can do that through like a firewall rule or some sort of exclusion. Just make sure that doesn't happen, because it can create huge problems, and if it's happening behind your back, you don't realize it's happening, it can be really hard to troubleshoot. Chunk size. So chunk size is basically, how your data gets split up into what size chunks, and it almost determines kind of the efficiency of balancing, or the amount of data that's going to be sent back and forth between your servers when balancing in a sharded setup. It also affects the frequency of splitting of overweight chunks. This is a pretty lightweight operation. It's basically just a metadata operation to the config servers, but it does affect the frequency of splitting of chunks. And also the number of chunks on any one server, or any one shard, I should say, is actually the identifier of whether or not that shard needs to be rebalanced. So whether or not some chunks need to be moved to a different shard in the cluster. So it affects several different things within sharding. Make sure your config servers stay up. When one server goes down, it prevents shard reconfig operations. That means any sort of splitting of chunks or any sort of balancing. Those are all metadata operations and need your config servers. When one config server goes down, then all of a sudden the config servers become read-only, so we can't do any metadata update operations to them. So it's very important to have them up. Another thing is use DNS CNAME. So use DNS to refer to the config servers. Otherwise, you have to restart every single MongoD and MongoS whenever you rename your config servers. So if you use something that abstracts the IPs of your config servers, or the names directly of your config servers, then you can avoid having to do all that when you rename your config servers, and it could possibly happen in the future. It's fairly easy to set up, so I recommend doing that. So shard keys. This is pretty interesting stuff, but when choosing a shard key, if you're interested in insert speed, you want to use a high entropy shard key. And what high entropy means is a mostly random shard key. This balances load across the shard. So when you want to insert, it's just basically randomly sending data to any one shard. And so it allows you to use all the shards you have for insert speed, for parallelism, basically. And this also kind of avoids migrations, because any particular insert has the same chance of going to any one shard at any one time. So it avoids any one shard from getting overloaded and should allow you to run without balancing. So for insert speed, scatter of documents is good. However, it's the exact inverse for query speed. You want to choose a low entropy shard key, so something that's mostly sequential. You want your range queries to hit one shard. So you actually want your queries to be most likely on the shard key itself, your range queries to be on the shard key itself. That way your queries will be hitting one actual shard, and that prevents the Mongo S from having to split up your query and then get a bunch of result sets back, stitch those together and send those back to the application server, right? All of that adds quite a bit of latency to your queries. So for your range queries, you want them to hit one shard. So scatter is bad when it comes to queries. Those are some quick and dirties for shard keys. And I will give credit for most of this stuff to Leif Walsh, who is one of the former Tokatech engineers and a great guy. So balancing. Balancing is tough because it's expensive. And the main problem is that it's a completely random workload. Everything relies on the shard key, which is a secondary key. As I talked about before, secondary keys create random workloads on the primary key. And the primary key is the way documents are stored. They are not stored in the chunk order or in the shard key order on disk. And so the three biggest operations are basically range operations on the shard key, which turn into completely random operations on the primary key. And they are a range query on the shard key for the chunks, right? You got to determine what's in the chunks because I'm going to move at the chunk granularity. I'm going to donate all that stuff. So I'm going to take it all, find all those documents. I'm going to donate them to the new shard where it's going. And then once all that happens, I update the metadata on the config servers. I'm going to do a range delete on the shard key. Again, a random operation on your primary key. On the donated shard, so the shard where the data used to be. So all of these things require tons of resources, and they're impactful to your production workload. So takeaway from this is that, one, you have to balance. So you want data to be balanced. You can't put it off for long periods of time because that only affects the amount of balancing you're going to have to do. And if you don't have a convenient time now, you're only going to basically sum up the number of workloads that you're going to have to do to balance. In the future, you're probably never going to have another good time. So sometimes you just have to figure out, when can I take this pain? And you can schedule balancing during low impact periods. I have in the resources, I have links to how you can schedule the balancer. So you can schedule your balance during low or lower impact periods to get it to run at certain times. It doesn't have to run at all the time or whenever it's determined that it needs to run by the sharding routers. You can also manually balance, but that is really difficult to do, and I do not recommend it at scale. It's very hard. So it's an option, but not one we're particularly going to discuss. But that's all I have for the presentation. That was about as quickly as I could get through that sharding section. So I am going to turn it over to Emily. I want to say thank you to everybody. Question time, by the way.
Thanks, John. Quickly, I wanted to mention that our Percona Live in Europe, Amsterdam, is coming up. If you haven't bought your tickets yet, now's a good time. And we're offering 40 euros off your registration using the discount code WebinarPlam, which is that slide there. So just wanted to quickly mention that. Also, so we will be now answering some of your questions. Please enter them in the questions field within the control panel now. If we cannot get to your questions today, there will be a follow-up blog post that John will be writing to kind of help address any of those questions that we couldn't get to today. And so with that said, one of our questions that came through, John, was, I've heard TokuMX has less lag to the point of being able to read off of secondaries pretty reliably. Is that true?
Yes, it can. Obviously, that always depends on the use case. And TokuMX can suffer from the same thing. Some applications are extremely high throughput, and you may need to actually do something, micro sharding or sharding to get more replication streams. But in general, especially when compared to the memory map engine, TokuMX does replay on your secondaries much faster, to the point of often getting to zero lag, which means you don't have to worry about different different versions of documents between your primary and your secondary. So yes, that is true, but it does depend.
Okay, great. Well, look, we've got a couple more questions trickling through now. You talked about TTL for indexes, and what about a fixed size of memory and eviction algorithms like LRU? Does Mongo support it?
So I don't completely understand that question, but so TTLs function the way TTLs function, and that's it, right? The TTL thread works one way, and that's it. You could use, if you wanted to do an LRU type of thing to expire data with a TTL, you can use that expired at field. That could kind of, with certain application logic, get you probably what you're looking at.
Okay, great. Our next question is, what are the challenges that should be kind of considered while upgrading from MongoDB to WiredTiger?
So upgrading to WiredTiger from MongoDB, well, that's not necessarily an upgrade. So WiredTiger is part of MongoDB, right? It's a storage engine now with the new storage engine API that MongoDB has. So upgrading, well, first of all, I guess you need to know that you're going to have to dump and reload your data, right? Because it's completely different on-disk data structure. And also right now, per MongoDB process, there's only one storage engine that can be used. So it's not like MySQL, where you can have a different one per table. You actually have to use one per MongoDB. So you're not going to be able to use memory map and WiredTiger. You have to choose one or the other. So that's something that you should need to know.
Okay, and we'll do one more question before we wrap up. Can we use TokuMX as a drop-in replacement for MongoDB?
TokuMX currently is a drop-in replacement, so it uses all the same wire protocols, uses the same drivers. It uses basically everything else you would need, all the same language. It's MongoDB, but what happened was we took out the storage code and we bolted in the fractal tree basically into MongoDB. Right now it's compatible with version 2.4.10, I believe it is, of MongoDB, so it's a little bit behind, so you won't be able to use some of the new features 2.6 or 3.0. But we are developing TokuMX SE, which is a storage engine for MongoDB 3.0. So you will be able to use kind of some of the cool things of the fractal tree, but without some of the added cool features that TokuMX has. So think of TokuMX SE kind of as TokuMX Lite.
Great, thanks, John. So with that said, I think that concludes the end of our webinar. I want to thank everybody for attending today's webinar. Scaling MongoDB, avoiding common pitfalls. And I want to tell everyone to have a great rest of your day. And thank you, everyone, for attending.